We will have demonstrations of the workflows, and you can follow and try to follow on your computer. I will now start with the first example using the physiologically based kinetic model.
A PBK model represents the human body as a set of interconnected compartments, describing the absorption, distribution, metabolism, excretion after exposure, either oral, by inhalation or dermal, to a chemical and or its metabolite within the body. This model takes into account physiologically, physicochemical, and biochemical parameters. The purpose of the PBK model is to simulate the concentration profile of chemicals of interest in time, in blood, and in organs. The applicability of such model, for instance in risk assessment, is to perform several types of extrapolation, such as high to low doses, route to route, in vitro to in vivo, acute to chronic toxicity, and from single to repeat exposure. Here we can see on the right side that there is a summary of all the chemicals for which we developed PBK models and for which exposure route was developed, so either oral, dermal, or inhalation. These models were then implemented into the KNIME workflow. You can see an example of such a workflow in the picture on the left. You can see that the architecture is quite complex. Thus, to make it easier for users, we have made a web version. So let's have a look on how to execute the workflow via the Cosmos KNIME WebPortal. In order to access, you need login details, which you will get once you have registered to the Cosmos space. Once you have logged in, you can see that the main page is divided in two parts. On the left, you have a dropped list with all the different fields for which Cosmos developed workflows and models. So if you want to run the PBK model, you have to go under biokinetic, you select physiologically based kinetic, and you select the chemical of interest. You then will get on the right side displayed a short description of what the model can do, and you can select start. You will have here to input some data, so the range of time that you want the model to simulate, the steps, all of these are in hours, the dose, which is in milligram. In case you have a dermal PBK model to run, you need to also input the volume of your lotion, so in milliliters. And then you can select one of the 7 models that we have developed. So 4 are for dermal, 3 for oral. 6 of these models are based on human data, and 1 on rodent, on rat. Of this human, 1 was based only on in vitro data found in the literature. I will select today the human oral. I will shorten up the time to 24 hours and increase the dose to 100 milligram. I will then press next in order to execute the model. So in a few minutes, you actually obtain a graphical results of time versus concentration for caffeine and its metabolites in liver, in lungs, and in blood. And if you scroll further down, you also have a report which you can download, where you will find a stable summary with all the maximum concentration, Cmax for liver, lungs, and blood at that dose selected at the beginning, and also the area under the curve obtained by the simulation. You also have, again, the graphical representation, and at the end, you have the concentration and the time. For each time point within 24 hours, you will have the concentration at that time point, 0.1 interval. You can then download a report, and here have all the different options. And with this, you can further use the results for other analysis.
The next example will be about the virtual cell-based assay.
The virtual cell-based assay consists of ordinary differential equations represented by 4 sub-models: a fate model, a cell growth model, and a toxic effect model. The purpose of the tool is to simulate the fate of a chemical and the intracellular concentration leading to the effect and to cell perturbation. For more information, I would like to encourage you to download the relevant documentation from the Cosmos space. We can see here on the left, the KNIME workflow that was developed to include the virtual cell-based assay, and on the right side, a table summarizing the chemicals for which now the virtual cell-based assay web portal version can simulate, and the different type of cell lines in single and repeated exposure. So now I would like to move to the Cosmos KNIME web portal for a short click-through session. In order to access the Cosmos KNIME web portal, you need to register and to get your access detail. Then once you logged in, that the main page is divided in two parts, and by selecting the repository file public, you can then access under the biokinetic file the virtual cell-based assay model. By clicking on the virtual cell-based assay, the VCBA, you can see on the right side that a short description of the model will pop out, and then you can click Start, and you will have the possibility to input some parameters, so to choose which type of cell line you would like to simulate, which type of chemical, for instance today caffeine, which type of exposure, single, repeated, or you can also try to optimize the parameter or validate your model. You need to input also the number of cells, the time of your incubation, so usually 48 hours or 24. You can select the assay volume which you used in your in vitro testing. And if you are in the repeated exposure mode, you can also have to input these last three parameters, such as the initial concentration, the interval time, and the number of exposures. Finally, you must introduce the concentration used in your in vitro testing. Then you press Next. You wait that the workflow will execute. It will take around 5 minutes. So here you have displayed the results, and you will see that you will have 4 types of graphical outputs, and these graphical outputs also will be available in the report version, which you can download as a PDF, a doc, or any other type of file.
Hello everybody, let's go on with the demonstration of the workflow that we have developed within the Cosmos project. And I will focus now on the workflow that we developed for nuclear receptor binding and absorption. Okay, I will give first a brief background on the computational tools that we have developed. Then I will show you how these tools were automated into KNIME workflow, and I will show you the different workflow that we have developed, and then we move on the hands-on session directly on the web portal. So just to give very brief background on the computational tools that we have developed, within Cosmos we developed several tools focusing, trying to addressing different issues. So an important issue addressed within Cosmos was the analysis of the chemical space of chemicals, and particularly focusing on cosmetics. Then, as we have seen this morning in the presentation of Elena, we work on developing in silico tools by employing different approaches and modeling methodologies to support the toxicity prediction in the adverse outcome pathway framework. And we did this by modeling initiating events that are involved in in the K pathway leading to repeat dose toxicity. So, for example, liver steatosis, as we have seen this morning. And then also Q-star models were developed for the prediction of oral and dermal absorption, and this was done to to support the oral to dermal extrapolation, and I will explain better later. And finally, as Alicia already explained, we developed several models to support the biokinetics prediction and in vitro to in vivo extrapolation. So starting from the workflow for chemical space analysis, just to give a brief background. Chemical space analysis is quite a challenging issue to analyze, can be studied from many using different approach. In our analysis, we regarded the chemical space of a data set as the range of physicochemical properties and structural features that are covered by chemicals that are included in a data set or in a chemical inventory. The analysis of the chemical space of a data set over a chemical inventory is a very important step when developing in silico modeling. This can be useful for preliminary explorative analysis of datasets. It's useful to perform comparative analysis among different datasets, among different inventories, or if you want to explore the differences between different classes included in a dataset. And of course, also for the assessment of the potential application of any computational tool when we want to apply these tools to new chemicals. In the workflow that we developed for the chemical space analysis, this workflow was aimed to perform an explorative analysis of basic physicochemical properties and structural features of one or more data sets by combining multiple approaches and multiple descriptors. In our workflow, we perform different kind of analysis. So we perform distribution analysis and calculation of basic statistics on individual properties, mainly physicochemical properties of the data set. Then we analyze our data set by using principal component analysis on selected sets of physchem properties and descriptors. And in the workflow that we've developed, we were using paddle descriptors, since these are freely available. These can be calculated by freely available tools, but of course, using the desktop version of the workflow, the user can also implement also nodes using commercial tools such as Dragon or Moses or other descriptors. And then the workflow also perform profiling of structural features, and this is made by calculating the frequency rate of different structural features that can be chemotypes or functional groups within a data set, and focusing the attention mainly on those structural features that are mainly able to discriminate different classes within a data set, such as active or inactive. This is how the workflow looks like in the desktop version. You start first from a data set input, so you can input one single data set that can be maybe characterized by different classes, or input more data sets and then combine. Then you calculate the descriptors, so physchem properties, 2D descriptors, and chemotypes or functional groups. And then the workflow split in two main branches. So we have the physchem, the analysis of the physicochemical space, and this is done by distribution analysis and principal component analysis on a subset of physchem properties. Then you perform an analysis of the 2D space by principal component analysis. And then you have the profiling of the structural features. And these are, as the output, you will have a report with different plots, so the classical plots of principal component analysis, frequency profiling, distribution analysis, and also you can download also the values of the descriptors and the frequency rates of different descriptors. We have developed also a web portal version for this workflow, but it still needs to be finalized, so we will not see it today, but we are also, this will be available soon by the end of the project, and also all the user guides on how to run this workflow, both in the desktop version and in the web portal version, will be available through the Cosmos page. Moving now to the workflow developed to support the prediction of nuclear receptor binding. We have seen this slide this morning with Elena. So as we have said this morning, what we did was to develop tools to support the prediction, to provide prediction for nuclear receptor binding, since this has been identified as an important initiating event in the development of liver steatosis. We developed different in silico tools by employing different modeling approaches. So this morning we have seen the molecular modeling approaches, but we also developed some QSARs, for example, for the prediction of helix star binding, and for QSAR for the prediction of PPR gamma activation. And also a workflow was developed for the screening of potential nuclear receptor ligands based on structural alerts and physicochemical rules. And the final aim was to combine all the different predictions obtained by different approaches by applying consensus modeling and data fusion methods. When feasible, the models that have been developed have been also implemented into KNIME workflows. And I'm talking about the classification model for the prediction of helix star binding, and of course the workflow for nuclear receptor ligand screening. So starting from the prediction of helix star binding, just to give you some background on the model, then we will see how to run the model on the web portal. So we developed two QSAR classification models based on partial least square discriminant analysis classification methods. And these two models are based on two different sets of descriptors calculated by free available software that are PADEL and RDKit. The models were developed and validated according to the OCD principle for QSAR validation, and also the applicability domain was defined by using two different approaches that are the leverage approach and similarity approaches. And the analysis of the applicability domain is important to assess the reliability of prediction, since we want to know whether the target compound is into or outside the applicability domain of our model, in order to see whether the prediction can be reliable or not. This is how the workflow looks like in the desktop version. So first, you have the first part dedicated to data input. So you can input your target compound by drawing it, or you can import in batch using SMILES, using a CSV file or SDF file. Then you have a part of the workflow that calculates the descriptors. So we have two workflows, one based on PADEL and one based on RDKit descriptors. Then run the QSAR model, and then you got the model prediction as active or inactive, where active in our case means potential helix star binder, or inactive, that is potential not binder. And then applicability domain, where you have information about reliability of prediction, so you will know whether prediction is reliable or unreliable. Okay, and now I will show you, we will see together how to run this workflow in the web portal.
To execute the workflow in the web portal, you have to enter the Cosmos 9 web portal page and log in. To log in the Cosmos 9 web portal, you have of course to be registered, and there is a link below that explains how to register. Once you have logged in with your credential, you will find the public folder. So look for your workflow on helix star binding potential. As you can see here, these are the two workflows implemented, the two QSAR models, one based on PADEL descriptor and the other one based on RDKit descriptors. In this tutorial, I will show you how to run the model based on PADEL descriptors, but these are exactly the same. So select the workflow of your interest. In the first page, you will find a summary description of the workflow and an explanation and the input files. In particular, you can input your target compound by drawing it, or input more chemicals in batch using a CSV file with SMILES, or input an SDF file. If you're using a CSV file, pay attention to use this specific format. So you have to include just two columns, including molecule name and SMILES, and use these separated by comma, and use these specific column headers. To run the workflow, just click on Start. Okay, you are asked the type of the input format. So you can draw a molecule, read a CSV file, or read SDF file. In this case, we will draw a molecule. So click on Next. Draw your molecule here. We'll do just a simple example. And then click on Next. This is the output page where you will find a preview of the final report, including the prediction for your target chemical, so molecule name, the structure of the chemical compound of the target compound, and the prediction. In this case can be active or inactive, where active is potential LXR binder or inactive not binders. Then you will find the values for the descriptor calculated for your target compound and the information on the applicability domain. You can download this report in different formats, such as PDF. You can also input your chemicals in batch by, for example, reading a CSV file. Click on Next. Select the CSV file, click on Next again. Now the workflow is executing. And here again you will find the PDF, the preview of the report, including the prediction that you got for the target chemicals, so as active or inactive. Again, you can download the report as PDF file, and you can download the QSAR prediction and information on applicability domain. You find also here a link to the Cosmos page, where you will find all the documentation related to the QSAR models, including model development and performances, as well as user guides on how to execute the workflow in the KNIME Analytics platform and in the web portal.
In this context of predicting nuclear receptor binding, we have also developed a workflow for the screening of potential nuclear receptor binders to nuclear receptors that are involved in the development of liver steatosis. And we can show you a non-live demonstration of the tutorial that we are also developing for in which we explain how to run the work in the web portal.
Nuclear receptors are an important target in toxicology, in particular when dealing with repeated doses. They are associated with fatty liver. Hence, the workflow is designed for screening potential nuclear receptor ligands. Our modeling approach is based on activity data from Campbell and ligand-protein interaction data from the Protein Data Bank. These have been selected for all relevant nuclear receptors. Ligands have been identified based on combinations of structural and physicochemical features for each nuclear receptor. Below we see an example of the retinoic acid receptor. We see physicochemical informations like how many rotational bonds there are or what's the molecular weight, which kind of describes the applicability domain or the physicochemical properties of ligands or potential ligands. Furthermore, these compounds need to have certain structural features which are expressed with smarts codes or with visualization of smarts codes on the right side. Principally, we have done this approach for a variety of nuclear receptors, and the compilation of all those little sub-workflows we can see here. So every color represents a nuclear receptor or a compilation of very similar nuclear receptors. Here, for example, we see a retinoic acid receptor and the retinoid X receptor. Or here we can see the LXR, the liver X receptor. So let's have a look on the KNIME web portal how to use this workflow. First, we need to log in. Therefore, of course, you need to be registered. There's a link below which explains how to register. So, after putting in your username and your password, you click on Login. And you look for the workflow. It's in Public, Nuclear Receptor Binding, Nuclear Receptor Ligand Screening, and here, this is the actual workflow. We just click on Start. So, principally, we can input a file. So if we want to run a batch of smiles, we can draw a structure from a compound. So let's start with the second one. So we just draw a structure of interest. And this compound should be picked up by certain nuclear receptor predictions. So this is our report. Here we see our abbreviations. So here we see the LXR means liver X receptor, and the VDR means vitamin D receptor, and so forth. And here we see our compound I just entered, and we see it's a potential ligand for retinoic acid receptor, retinoid X receptor, and the PPAR, which has, by the way, a little sub-workflow for fatty acids and retinoids, which have a certain potential for binding. So probably not relevant for when drawing a structure, but here we can download the report, for example, as PDF. So more relevant would be uploading a CSV file with SMILE, so a whole batch of compounds. The data needs to be in the following structure. So I've prepared a file with some actives and some non-actives. And we just press next. And here we see again the report. So the web portal version only shows us the active compounds. So the file contained 15 compounds, but only a few are actives, for example for retinoids, or this steroid compound. The desktop version gives you a complete output and shows you which compounds are inactive. However, you can get a printout if you click here on PDF. On Cosmos Base you find information about how the workflow was developed and how its performance is. And of course all necessary links are provided in the description below this video.
We'll move to the last part of this demonstration. So this is about the workflow that has been developed for the prediction of oral and skin absorption. First of all, we have said before, while we are talking about oral to dermal extrapolation, of course, the extrapolation of dermal toxicity from oral toxicity data is of particular importance when dealing with cosmetics. We want to estimate their bioavailability in human body, because cosmetics are mainly applied dermally. The majority of data available for these compounds are mainly oral toxicity data. Two factors are of particular importance when we want to assess the bioavailability of cosmetics. So we have to, in order to have oral to dermal extrapolation, the first factor is we have to evaluate the differences between the rate and the extent of absorption via the dermal and oral routes. And of course also we need to evaluate the differences between the metabolism in skin and liver. Focusing on the first issue, that is absorption, what we did within the Cosmos project was to collect available data for dermal absorption and for oral gastrointestinal absorption. And for the gastrointestinal absorption, we searched for PAMPA data, where PAMPA is an in vitro assay that is used to extrapolate and estimate the gastrointestinal passive absorption. We also performed a review of existing QSAR models for these two endpoints, and based on the collected data and the existing QSAR models, new QSAR models were developed, mainly re-implementing and improving already existing QSARs for the prediction of skin and oral absorption, and to allow then freely applicability of these QSARs. These QSARs have been implemented into KNIME workflow. Just brief background on the two models. So the QSAR model that has been developed for skin absorption is a very simple multiple linear regression model that is based on an update on the famous Potts-Guy equation. This model is based mainly on hydrophobicity and molecular volume, and this QSAR has been implemented into KNIME. We have seen the model and the workflow for skin permeability, so I think it's not needed to go through now in the web portal. But of course, if we can do it later. And then regarding the workflow for pampa permeability prediction, this is a multiple linear regression model that improves a model published by Nakao and co-workers. And this QSAR model is mainly based on log-D and topological polar surface area. Since log-D, there are not freely available software for the prediction of log-D. We developed two different QSARs based on calculated log-D. One log-D is used data available from CanSpider, and these data are log-D calculation by ACD Labs. And the other QSAR model is based on log-D calculated data from Chemaxon, and these data are available from Chemicalize. These two QSAR have been implemented in KNIME, and now Petko will show you how to execute this workflow using the web portal.
On the web portal, you have to log in with your username and password, which are obtainable from the Cosmos Space page. Once in the web portal, you can locate the pampa permeability estimation in the absorption folder and can start the workflow. First, you will see a short description of the workflow, the necessary input parameters, and the link to the complete description of the workflow. Now we will start it, and we are presented with the choice of the input form of our molecule. We can upload file with number of structures, put smiles in, or draw the structure. We'll go forward with our smiles. Now we have to supply log-D and the source of log-D, either ACD Labs or Chemaxon. We're going to Chemaxon, look for structure. Unfortunately, it is not available. Let's see what will happen if you remove a couple of hydroxyls. The structure is here, and we can see the log-D predicted by ACD Labs tools in the Properties tab. Here it is. But let's go with our original structure to Chemicalize.org. In general, to see log-D, we have to open all tabs. Now it is here. Unfortunately, we cannot get the number directly, so we have to save this image and digitalize it with our favorite digitalizing software. For demonstration, I have chosen a web-based digitizer. Here is our plot with the chosen point at 7.4 and on the line. Now we are viewing data 7.4, and Our log D is here. We are copying it and going back to our workflow. Chemaxon. Next. And we get our report page. On the report page, you see this mouse, the chemical structure, the log D source, the log D, which you have provided, calculated ratio of TPCA to molecular weight, and the predicted log PM. Also, you can see the reliability of prediction based on the extent of the extrapolation approach, and also you can see some details about the model implementations, about the variables, the equations, the statistics, and the observed versus calculated graphs. Additionally, you can download the numerical values from this table from the link of predictions. More information about the models and the workflow you can find at the Cosmos Space page, which is available at the description of this tutorial.
I think we have done with the demonstration. If you have any question about specific workflow that we have shown or the background of the model, please ask. Otherwise, you will find all the information, detailed information on the Cosmos Space, and tutorial will be available soon. And also additional workflow that are now to be now under finalization will be also available in 1 month. So we have also a workflow on ranking methodologies and the workflow for chemical space analysis. So these are going to be finalized very soon.